We'll be starting chapter 8 today on chemical reactions. And this is very much going to link back to things we did in the first semester in regard to formula writing, both ionic and covalent compounds. So through inquiry and exploration, you want to be able to differentiate between chemical and physical changes. That's something you can already do. We'll simply be reviewing it. We'll be writing and balancing chemical equations. You'll feel pretty confident with that today and more so tomorrow, assessed on it later in the week. And then later on in the week as well as next week, we'll be classifying and predicting chemical equations. So we'll talk about the different classes of chemical equations as well as when given reactants, predicting products. In the lab next week, you'll be conducting several different chemical reactions, analyzing the products, writing balanced equations, and looking for signs of a chemical change. Initially, we want to review some very simple concepts in regard to chemical changes and chemical reactions. Remember, when one or more substances is changed into one or more different substances, and the change involves atom rearrangement, you are going to have a chemical reaction. The law of conservation of matter says that matter is neither created nor destroyed in a chemical reaction, so we're simply looking at atom rearrangement. And examples of chemical reactions involving chemical changes includes the rusting of iron, digestion of food. Leaves change color up north in the fall because the amount of daylight decreases as well as the temperature. The chlorophyll breaks down, and as a result, some of the other pigments are exposed. Milk souring. You can't go back to where you started. If you have rust, you can't generate iron back. Once your food is digested, you're not going to see that bagel you had this morning. Once the leaves change color, they don't go back to green. They fall off the trees, and once milk sours, you don't want to drink it anymore because it's not the same substance. Chemical changes. Many lines of evidence of chemical change. We watched this video earlier in the year. If you want to go back and rewatch it, I've included the link for you. In that video, we saw energy being evolved as heat, light, or sound. So if you react two substances together and smoke is given off, heat is being released. You can determine if a reaction is endo or exothermic by looking at or measuring changes in temperature, whether the temperature increases or decreases. Many of you in elementary school reacted vinegar and baking soda together and you saw bubbles. Not this first lab, actually in both labs we will be generating a gas from two substances and you'll see the bubbles forming. Precipitate formation we looked at earlier in the year with the halide reactivity lab. We reacted, for example, sodium chloride with silver nitrate. We generated a silver halide. Most silver halides are precipitates. Solids form from aqueous solutions. If you have younger siblings, perhaps they take baths at night, and when they get out of the bath, and maybe some of you do as well, you get out of the tub and you drain the tub, and there is often a ring of soap scum where you initially had water and liquid soap. You get that solid caked on formation. I already mentioned that leaves change color up north when the chlorophyll breaks down, caused by the decrease in temperature as well as the decrease in the amount of day length. Many of you do eat nice healthy snacks like apples. You can peel the apple, cut it up. If you leave it out on the table, it will turn brown over time. If you seal it up right away, it's not exposed to air as much and the apple will keep a little longer, but even after a while, those things are not truly airtight and they will brown. Make sure you can differentiate between chemical and physical changes. Physical changes typically are your phase changes. Condensation and you probably saw quite a bit of condensation because it's been so cold out, and it really built up on the inside of the windows when it was in the 30s and 40s a few days last week. Melting, freezing, boiling, crystallizing, all phase changes, which are examples of physical changes. Be careful, there are more types of physical changes than just phase changes. Dissolving would be one, where if you dissolve salt in water, you have salt water, but you can boil off the water and get the salt back.
I feel like this is a weird thing, but you know how like when you get older, your like obviously your face like changes. Like, is that like a chemical change? Like, you get like wrinkles.
Yeah, but now there's all these great products where you can plump them back out, you know?
So, is that even like a physical, chemical, any of that? Or is that just...
It's changing your physical appearance.
It's changing your, right, the actual what you see is a physical property, but, so the question becomes, is the wrinkle caused because of a chemical change? I'm guessing it is, because they're going to inject something that's going to slow the process and perhaps drive it in reverse. So I'm guessing yes. But I have a great homework assignment for you. Why don't you look up the chemical reactions associated with aging and skin, and then we'll take a look at it tomorrow. All right. Maybe I'll let you work on it at the end of the period. That's a very good question. I'm going to guess it's chemical. It's a good question. All right, but be sure you'll see one easy multiple choice question on your test, not your quiz, in terms of chemical versus physical. And that gets back into chapter 1. One thing I do want to mention, just as an aside, only because I mentioned chapter 1, a lot of the kids want to lighten their loads, so to speak, in terms of their notebooks. You can leave, I would say, chapters 1 through 4 at home. I would hang on to 5. I would hang on to 5 and 6 in regard to formula writing only, in case you need to review that concept, and I would keep 7 for sure in the notebook, because we're going to get back to those types of conversions. But 1 through 4 for sure could stay home, and that will lighten up your notebooks, which are probably getting heavy. All right, so that's pretty much all the review stuff. What we really want to get into today is writing and balancing chemical equations. And when you write a chemical equation, you can go from a simple word equation, A and B, react to form or yield, C, D, and F, to a chemical equation where you have substances, pluses, and arrows only. So A and B, the and is replaced right here with the plus sign. So a plus replaces an and or a comma. React to form or yield is represented by the arrow. And it can say A and B react. Replace the react with an arrow. A and B yield to form. Replace that with the arrow as well. C, comma is replaced with the plus. D and F. We know reactants are the substances you start with. Products are what get generated or get produced. The arrow yields or reacts to form. Plus or comma and or comma are changed to a plus sign. For example, sodium hydroxide and hydrogen chloride react to form sodium chloride and water. This is where formula writing is going to come back very strong. Most of you have mastered formula writing. If you have not yet, you really need to refresh back in chapters 5 and 6, and please take the time to do that. Sodium hydroxide, chemical formula NaOH, and hydrogen chloride HCl react to form, represented by the arrow, sodium chloride NaCl, and water. You can see that the ands are replaced with pluses, react to form is replaced with the arrow. Covalent compound, ionic, ionic. This one is tricky, named as an ionic, but it is a covalent compound. Two or more nonmetals, covalent. Ammonia is NH3 and oxygen gas O2. And that one can be a little tricky. Let's go back and review your diatomic elements. This is the Brinkelhoff series. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. And remember, it spells Brinkelhoff. Whenever those are written, bromine liquid would be Br2. Solid iodine or iodine vapor, I2. Nitrogen gas, N2. Chlorine gas, Cl2. Hydrogen gas, H2, etc. So those are your Brinkelhoff series, your diatomic elements. Be careful with those. They will come back to bite you a little bit when we get into single replacement reactions. Be careful there. So we'll replace the oxygen gas with O2. React to form the arrow, nitrogen monoxide, a covalent compound, and water. What you see in this equation are numbers before substances. Those numbers are known as coefficients. They are whole numbers, not zero. There are no coefficients of zero. And they will indicate the relative amounts of reactants or products. Typically, they represent moles. 4 moles of ammonia react with 5 moles of oxygen gas to generate 4 moles of nitrogen monoxide and 6 moles of water. If the substance is a gas, it can also represent volume, and we'll get into that later on. If there's no coefficient, it's a coefficient of 1. So if I say, what's the coefficient of sodium chloride, you would tell me 1. If I said, what is the sum of the coefficients in this balanced equation, you would say 1 plus 1 plus 1 plus 1 is 4. So in this equation, what's the coefficient for nitrogen monoxide? 4. What's the sum of the coefficients? 19 is correct. And those are the types of questions you can see in a multiple choice format. All right? The other thing you may see in a balanced chemical equation is the state of matter. So solid zinc. Chemical symbol for zinc is Zn. Solid represented by the capital S in parentheses. Oxygen gas. G in parentheses indicates that the state of matter is a gas. It's not for grams here. Be careful. Solid zinc oxide, S. Other symbols you can see. S for solid, Cr, crystal or crystalline, that's a solid. L for liquid, G for gas, AQ for aqueous, where the substance is dissolved in water. A little bit about energy, and then we'll get into balancing equations. Energy is anything that is not matter but can cause a change in matter, and you'll see that energy is neither created nor destroyed in a chemical reaction. You can get the release or absorption of energy, but it's released from either the system or the surroundings, and it's absorbed by the other one as well. Kinetic energy, you'll remember from middle school, deals with energy of motion. It can be calculated as 1/2 times the mass times the velocity squared. We're not going to do that. Potential energy is the energy associated with storage. And again, you've seen this in middle school. We're not really going to deal with it here. In an exothermic reaction, energy is released during the chemical reaction. Typically, we find that this type of reaction yields stronger bonds than those of an endothermic reaction. So the products will have stronger bond formation, if you will, than in an endothermic reaction. Exo means outside, therm for heat, exothermic as if the energy is exiting. And you'll see that exiting here. In an exothermic reaction, energy is going to be on the product side of the equation, either written as E or energy, or the quantity of energy provided. Kilojoules or joules is a quantity of energy. So when you generate rust from iron and oxygen, 824 kilojoules of heat is released. It's released because it's exothermic. It's on the product side of the equation. Alternatively, the equation could be written, instead of this term being here, it would indicate that the delta H, the change in enthalpy, is negative. A negative delta H is indicative of an exothermic reaction. In contrast, chemical reactions that absorb energy are endothermic. So energy is absorbed, listed as a reactant, or the quantity as such. This is the decomposition of dinitrogen pentoxide generating dinitrogen tetroxide and oxygen gas. This is an endothermic reaction because energy is listed as a reactant, or alternatively, instead of having this term here, the delta H would be indicated with a positive value. Now, don't be confused here. Even though this is exothermic with a negative value, you do still add the amount, but to the product side. Here it's on the reactant side. Exo versus endothermic. And you'll see later in the chapter that different classes of reactions typically are exo or endo, and we'll talk about that later. I mean, typically in a decomposition reaction, you're busting it up, like breaking up with somebody. That requires energy, endothermic. What we want to get into today is introducing balancing equations. Once you practice, you'll be very good at it. I think some of you already know how to do it. With conservation of mass in atoms, as we talked about in Chapter 2, Lavoisier talked about the law of conservation of mass, where mass is neither created nor destroyed in a chemical reaction. And you'll see this, for example, right here, and then I'll go over number 2 that's listed. You can see that mass is conserved. When carbon and oxygen gas react to form carbon dioxide, we can get the atomic masses of the element from the periodic table. We've got 2 oxygen here, so 2 times 15.999 gives you 31.998 AMU for the oxygen gas, the diatomic element, and then 1 carbon and 2 oxygen, and you have a mass of 44.009 AMU for carbon dioxide. The sum of the masses of the reactants is equal to the sum of the masses of the product, so mass is conserved. That you saw back in Chapter 2. What you're going to see here is that the numbers and types of atoms present in the products are going to be the same as those in the reactants. So if you consider this chemical reaction, on the left side of the reaction, the reactants, we have 1 carbon and 2 oxygen. On the product side, we have 1 carbon and 2 oxygen. So the number and type of atoms is going to be conserved. And that's what you will need to balance an equation. That's what we're going to check. The steps to balancing equations are listed here. We'll read through each of these steps, but until you actually do it, it may not quite come together for you. First thing you always want to do is write the chemical reaction, replacing words with symbols or formulas, reactants on the left, products on the right. When you first get started balancing equations, I like to list the elements involved in the reaction and count how many there are on each side of the equation. Now, elements is listed there in italics because sometimes I just write a single atom and sometimes I'll write a polyatomic unit, and we'll talk about that. You're going to use coefficients, which are whole numbers, not zero, in front of the chemical symbols or formulas to balance the equation. If there's no coefficient, it's 1, not 0. That's a common mistake that kids make. And under no circumstances will you change the subscripts. Be very, very careful there. As we already mentioned, the coefficients will tell you the proportion of each substance to one another. Always start beginning your balancing with an element that occurs only once on each side of the equation, and you'll get a feel to where to start as you work through. When you want to figure out how many atoms you have on each side of the equation, you're going to multiply the coefficient by the subscript or subscripts. We'll take a look at that. If you have a polyatomic ion on both sides of the equation and those elements are not appearing anywhere else in the balanced equation, keep the polyatomic ion unit together. I'll show you that as well. Typically we do elements such as H and O last, especially if they occur in multiple reactants or products, and I'll show you that as well. When you want to balance net ionic equations, you've got to check for charge balance. We're not going to get into that in this chapter. We'll come back to it later on. And then at the very end, it's important that you make sure your coefficients are the smallest whole number ratios possible, because if they're not, you'll need to reduce them down, and we'll take a look at what happens there as well. The first two examples are done for you in your notes. I'm going to work through them on paper so you can watch the derivation. I would just watch these initially, and then we'll work a whole bunch of problems together. We'll start with the easier ones today. We'll work on the tougher ones tomorrow. You'll get some good practice time in tomorrow, and you'll be ready for your quiz later in the week. In the first example, I'm given this equation showing the generation of salt from sodium and chlorine gas. And again, this is given in your notes with a table, so I just want to keep it simple. Now, as you get good at balancing equations, you're probably not going to make this table. I make it in certain instances when I see that an equation is going to be tricky to balance. We've got sodium and we've got chlorine. So I list each atom separately. Every time I have a capital letter, I have a new atom. R for reactants, P for products. I've got 1 sodium on the left and 2 chlorine on the left. I've got 1 sodium on the right and 1 chlorine on the right. In order to be balanced, the sodium have to be the same, the chlorine have to be the same, and they're not. You've got 2 chlorine here. To balance this, I'm going to put a coefficient of 2 here. And I've got 2 sodium and 2 chlorine. Now my chlorine are balanced, but my sodium is not. What should I do? Coefficient of what here?
2.
You got it.
Wait, so you can just put it to
Yep. What's the coefficient of the diatomic element? 1 is correct. What's the sum of the coefficients in the balanced equation? 5 is correct. Good. The second example is a little trickier, and we'll get into these combustion types of reactions for balancing in more detail tomorrow because they are trickier. In a combustion reaction, you have a hydrocarbon reacting with oxygen to generate CO2 and water. When I go to balance this, it's a little bit trickier. How many carbon on the left? How many hydrogen? How many oxygen? On the right, carbon, hydrogen, oxygen. And you'll see in these combustion, the CHO always goes 1, 2, 3 on the right. When you balance combustion reactions, balance them C, then H, then O. So what am I going to put in front of the carbon dioxide?
3. Good job. Thank you.
Be careful with the oxygen. It's in multiple places. 3 times 2 is 6, plus 1 more is? Now balance the H. What times 2 is going to make 8?
4.
And now be careful with the oxygen. 3 times 2 plus 4 is?
10.
Correct. Last thing we have to do is the oxygen. What times 2 is 10? What's the coefficient of propane?
1.
1 is correct. And some of you are like, what's propane? Well, it's the one you don't know, correct? So what's the sum of the coefficients? 6 and 7 is? 13. No calculator on this, guys. You can do it. All right, let's take the next one. Here's your equation, which is in your notes. Again, you want to list each atom every time you have a capital letter. And that's how many of each you have, and I'd like to show you a trick.
Oh no, there's a 3.
So one thing that I would like to show you is when you have a 3-2 situation or a 3-4 situation, typically this will become the coefficient for the fluorine on the other side and vice versa. because that right away is going to make 6 fluorine on each side.
Oh. But then it's gonna make more.
Right, well, you've got to finish balancing. You've got 2 aluminum and 3 calcium. So what are you going to put in front of the calcium on the reactant side?
3.
And what's missing here?
2. Okay, I get it.
All right, I would like you to try this next one, which is very easy. You probably don't need a table. Actually, try both of them. I feel pretty confident you can do both of these.
Are we gonna always be allowed to do the table?
Yeah,
Okay.
but you're going to see, like, especially on the one I just gave you, it's probably not worth your time. I'll show you when it's definitely worth your time. But you need to do it. You do whatever you need to do to be successful on it. Try those two. How'd we do?
Pretty well.
No props? Yes? All right, and it just takes practice. I do want to show you a couple more problems, and then I'll give you a few problems to do tonight to make sure that you feel comfortable with this basic balancing, and then we'll get into some trickier balancing tomorrow with a tremendous amount of practice, and that'll get you ready for your quiz. In the next problem, this one has a polyatomic ion in it, and that's why, or at least one of the compounds is comprised of a polyatomic ion. So I want to show you a simple approach to work this type of problem. We've got sodium reacting with manganese 3 sulfite, forming sodium sulfite and manganese. And you'll learn later in the week that this is a single replacement reaction. Now I see a sulfite unit here, and I don't see S's or O's anywhere else, so I'm going to keep that as a unit. I'm going to have sodium, manganese, and that's why you'll see sometimes I write atom with a star, because this is going to be a unit, if you will. I've got 1 sodium on the left, 2 manganese, and 3 sulfite units. I've got 2 sodium, 1 manganese, and 1 sulfite unit. If there's no parentheses, you have 1 unit of it. And when I balance this type of equation, I will start with the polyatomic ion. I need 3 of them on this side, and that's going to make 6 sodium. I'll put a 6 in front of the sodium to generate 6 here, and then finally a 2 here. And you have a balanced equation. And again, it requires some practice. I would like you to try this one. Even though you have a polyatomic, you're not going to treat it as such because it's busted up. And this one may look hard at first glance, but you're going to see it's very easy. Give it a shot. And to balance this one, what do you need?
A 2 on the box.
Very straightforward. All right, so the balancing of the easy ones I think will be very, very basic for you. The combustion ones are a little harder. I just want to show you 1 or 2 more examples. In the next example, you're given words. You first have to write the equation and then balance it. And this is where your formula writing will come into play. It says sodium phosphate reacts with iron 2 chloride to form sodium chloride and iron 2 phosphate. And then you want to balance that one. You'll get a sec. You'll get a few minutes. And the next one's tricky too. So that was the equation I just wrote. And I'll let you balance that in just a minute. The next problem is tricky as well because it says fluorine gas. How do you write fluorine gas? F2, good, it's diatomic. Vanadium 3 iodide. vanadium 3 fluoride. And how would you write iodine? I2. And take a few minutes to try and balance those. We'll give it a look-see. And then on the classwork I'm going to give you, I'd like you to try and do 1 through 10 tonight. If you come across one you can't figure out, just leave it. We'll work it tomorrow. But this will give you a little bit of balancing practice. We'll do some more problems next time, especially the more complex ones, and then I'll give you most of the period to practice getting you ready for your quiz. So give it a shot. And I'll pop the answers up there to make sure you have it cold. And again, initially you're probably going to use the table. As you get better at this, you probably will forego, although there are still some problems that I think are so tricky that I'll always go back to basics and use my table. In Introduction to Balancing Equations, you'll be very good at this with practice. Just have the patience with it, and I know you'll be very successful with it. We'll continue with balancing tomorrow, and you will have a much better foundation for writing and balancing chemical equations. I think you'll feel very comfortable with it. The quiz is very easy, and you'll get started in this third 9 weeks very well. Question?